It's Paul Bamberg back with the third and perhaps most interesting of these MathE3 videos. I'm going to try to show you some examples that will indicate to you what the central limit theorem means in practice. I'm not going to attempt to prove this difficult theorem. To start, I want you to think about the variance of sums and means of random variables, particularly of what are called independent random variables, cases where the probability involving one of those random variables has no connection with probabilities involving the other one. In my example, the random variable x will simulate the sum of n rolls of a fair die, while the random variable y will represent the result of selecting 25 random numbers from a standard normal distribution and adding them together. It's fairly reasonable that the expectations add up under these circumstances, but it's quite counterintuitive that the variances, which involve squaring, also add up. Nonetheless, it's true. The variance of the sum is equal to the variance of x plus the variable variance of y. So we're going to try this with a large number of samples, 10,000 to be precise. I'm setting up x, y, and z as vectors with 10,000 empty slots to hold the result. And as we go through, in the ith slot for x, I will sample from 1 through 6 10 times with replacement, and then form the sum, thereby simulating the sum of the rolls on 10 dice. In the ith slot for y, I will store the sum of 25 samples drawn from a standard normal distribution, and then I will store the sum of those two quantities in the ith slot for z. Let's have a look at what we've got. If you just look at the first entry in each row, we got 43 for our sum of n die rolls. We got 2.77 and change for the sum of our 25 random variables. And for the sum, we got 45.77 and change. That's the sum. Not a big surprise that the mean of z and the sum of the mean of x and the mean of y come out exactly the same. What is a bit of a surprise is that if I compute the variance of z, I get very nearly the same result as the sum of the variance of x and the variance of y. In terms of probabilities, these quantities are exactly the same, but what we're doing is looking at 10,000 samples, so we shouldn't expect perfect agreement with theoretical results. Now, if x and y both have normal distributions, not only are these results still true, but the sum of the two random variables z also has a normal distribution. This is a property that's peculiar to the normal distribution, and basically it explains why normal distributions show up in so many different contexts. So we'll do the same simulation, except that this time x will be a sample from a normal distribution with a mean of 3 and a standard deviation of 2. That means the variance is 2 squared or 4. Y will be a single sample from a normal distribution with a mean of 5 and a standard deviation of 3. And z will be the sum of the two things. That will have an expectation of 3 plus 5 or 8. And my claim is that we'll have a variance of 4 plus 9 or 13. Let's see if my claim is correct. I look at the histogram of z. Looks pretty much like a normal distribution, doesn't it? And now let me do a plot of the density function for a normal distribution with a mean of 8 and a variance of 13. Fits perfectly. So, important result to remember. The sum of two independent normally distributed random variables is also normally distributed, and the expectations and variances add up. Think about what would happen if you added n of these variables together. If you add together n independent variables, you will multiply the expectation by n, and you will also multiply the variance by n. If instead of adding you average, you multiply the expectation and variance by n, but then you divide the variance by 10, and you leave the expectation unchanged. Since adding two random variables that are normal leads to another normal random variable, the same thing is true for n of them. So if you add or average any number of independent normal random variables, you get another normal random variable. What does that mean? It means that if we take the sum of 100 standard normal random variables, each with a mean of 0 and a variance of 1, we should get the same effect as if we took a single sample from a normally distributed random variable with a mean of 0 but a variance of 100. Let's try it. In X, we will store the result of adding together 100 random variables, each with a standard normal distribution. In Y, we will store a single sample drawn from a normal distribution with a variance of 100, that is, with a standard deviation of 10. There's a histogram of X. Using add equals true, I will overlay the histogram for Y in green, and you can see they're almost exactly the same. Not exactly the same because we only took 10,000 trials, but pretty close. And they both agree nicely with the probability density function for a normal distribution with mean of 0 and variance of 100, standard deviation of 10. What the central limit theorem says is that this same phenomenon occurs even if you don't start with a normal distribution. If you take the sum of enough random variables, all of which have the same distribution, then the result will have an approximately normal distribution. So let's try this. The roll of one die is equally likely to produce the numbers 1, 2, 3, 4, 5, and 6. And if I take the expectation of that, I get the average of the numbers 1 through 6, which is 3.5. If I take the mean of the square minus the square of the mean, I get the variance, which is a little bit less than 3. Now let's try doing this 10,000 times. So in the ith slot, there are 10,000 empty slots waiting to hold these results. I get the sum of 100 samples, each simulating the roll of a single die. Let's plot a histogram of that. Well, for a single roll of a die, that histogram would look flat, but this does look mighty normal, doesn't it? And for comparison, I will take a density function for a normal distribution with a mean of 100 times 3.5, which matches, and a standard deviation, which is n, that's the square root of 100, times the square root of that variance I just calculated, and it matches perfectly. That's a simple example of the central limit theorem. The usual way of stating this involves subtracting off the mean, getting rid of that 350, and dividing through the square root by the square root of the variance, which is n times the variance for one individual die. That should give us a variance of 1. So let's do that. Exactly the same as before, except this time I subtracted off 350, then divided by 10 times the square root of v. There's a histogram of y. And there is a plot of the standard normal distribution, which again matches up remarkably well. There's absolutely no requirement that the distribution with which you start have any sort of symmetry. So you might imagine playing a game where with a probability of 1/4 you lose $10, with a probability of 1/4 you lose $5, with a probability of 1/4 you win $1, and with a probability of 1/4 you win $14. This is a fair game because your expected payoff is $0. Let's make a little vector in R to allow us to simulate this payoff, calculate its mean. The mean is 0. It's a fair game. And I can calculate the variance by having R compute the mean of the square and subtracting off the square of the mean. There's the variance, which is about 80. Now, if I play this game only 4 times, the result is nowhere near normally distributed. Let's check that with a simulation. 10,000 times, I will take the sum of 4 samples drawn from this payoff with replacement. I will divide by 2 times the square root of v in an attempt to make the variance equal to 1. And let's see how well I've done. Well, that doesn't remotely resemble a normal distribution, does it? On the other hand, I have made the mean almost precisely 0, and I've made the variance very close to 1. What hasn't happened is I haven't ended up with a normal distribution. There's a normal distribution with the same mean and variance. The two distributions don't look at all the same. However, if instead of playing 4 times I play 100 times, the result will be very nearly normally distributed. So let's repeat with one small change. The one small change is I'm now adding together 100 samples, and to make the variance of the sum get reduced to 1, I divide by the square root of 100, 10 times the square root of v. And that does look consistent with a normal distribution. The mean and variance are close to 1, and if I overlay the density function for the normal distribution, I've got a pretty good match. Let's try again with a different distribution. This time I'm going to draw random numbers from a uniform distribution in 0 to 1. That is, any number in the interval from 0 to 1 is equally likely. Clearly, the expectation is going to be 1/2. What's not at all obvious is the variance is 1/12. Trust me, I've calculated it. So I'll store 1/12 in v. And the same thing happens. If I take only a small number of samples and add them together, I don't get a normal distribution. Let's try with 2 samples. R unif draws a random number from a uniform distribution, and R unif followed by 2 in parentheses gets us 2 samples to add together. If I divide by the square root of 2 times v, that should reduce the variance to 1. Let's see how I've done. Well, the distribution doesn't look normal at all. On the other hand, I have succeeded in getting a mean that's close to 0 and a variance that's close to 1. Now let's try with 100 samples and see how we do. With 100 samples, I have to subtract off my expected mean of 50, and then I have to divide by the square root of 100 times v. And now this histogram is looking very much like the histogram for a normal distribution. Furthermore, the mean is close to 0, the variance is close to 1, and there's the demonstration that the overall distribution is very close to normal. And that's what the central limit theorem says. If you take either the sum or the average of a large number of random variables, a rule of thumb is large means 30 or more for a symmetrical distribution. Large probably means in the hundreds if you have a wildly unsymmetrical distribution. And all these random variables have the same distribution, which you don't need to know. Then the resulting random variable has a distribution that's approximately normal, and by rescaling it appropriately, you can make the mean be 0, the variance 1. You can turn it into a standard normal distribution. And for that reason, in real-world situations where you're getting a random variable that's plausibly the result of summing or averaging a lot of independent random variables, it's a reasonable assumption that the random variable that you've created has an approximately normal distribution. It's that property of the normal distribution that makes it the most important of all probability distributions.